Hey, welcome back to your favorite calculus class. We'll take a look here at some more concavity and curve sketching here. We'll put all the information together. First of all, we've got this y equals x times x minus 2 cubed. Let's go ahead and take the first derivative so we can find the critical points and where it's increasing, decreasing. I'm just going to go ahead and use a product rule. So derivative of the first times the second plus the first times the derivative of the second. So it looks like our first derivative here, if I factor out an x minus 2 squared, I'd have an x minus 2 from that first term there, and then a 3x. So our first derivative here is x minus 2 squared times x 3x plus x is a 4x minus 2. Go ahead and see where derivatives equals 0 or undefined. There's nowhere where it's undefined, but I do get a critical point at 2. Notice that that is defined in the original function. And from here I get x equals 2/4 or a half. So here's our critical points. Let's go ahead and run the first derivative test with a half and 2. Let's throw in, how about y prime of 0? So I'd have 0 minus 2 squared times 4 times 0 minus 2. Negative 2 squared is a positive. 0 minus 2 is a negative. So this is negative. So the original function must be decreasing. Let's throw in like a 1. I throw 1 into the first derivative. And again, I'm throwing it in right there. I'll get that is positive, so the original function is increasing. Then I'll throw in 3, and it's also positive, so the original function is increasing. So our critical numbers here are a half and 2. We're increasing from a half to 2, and then from 2 on. We're decreasing from negative infinity up to a half. We have no relative minimum. No relative maximum. We do have a relative minimum. We go down and then back up, so that would be at a half. I throw in a half into the original function, so a half times a half minus 2 quantity cubed. That will give us negative 27/16. And now we're ready to do the second derivative test and find our potential Hilbert numbers. So our first derivative here, first derivative is x minus 2 squared times 4x minus 2. So second derivative will be derivative first times the second plus the first derivative second. So we've got the double prime is, I could take a 2 and an x minus 2 out of each of those, and I'd be left with 4x minus 2 in that first term, plus over here I'd have an x minus 2 and 2. Remember, I factored out a 2 and an x minus 2. So I've got 2, I've got x minus 2, I've got 4x minus 2 plus 2x minus 4. So we've got 2x minus 2. I've got 6x minus 6. Let me take a 6 out front and multiply it by that 2, so I'd have 12 right there. Again, I took a 6 out of the 6x minus 6, right? So I'd have x minus 1. So there's our double prime. Notice we don't have anywhere where the double prime is undefined, so I'm just going to see where is this thing equal to 0, the second derivative, to look for our Hilbert numbers here. So my Hilbert numbers would be 2 and 1. Those are our Hilbert numbers. Make sure they're defined in the original to be Hilbert numbers. And now let's go ahead and run our second derivative test with that 1 and 2. And so let's throw in y double prime of 0. So I throw it into the second derivative. 12 times 0 minus 2 times 0 minus 1. I got 12 times negative 2 times negative 1. So y double prime is positive. So the original function will be concave up. Let's throw in like 1.5 into the double prime. That'll give us a concave down. And let's throw in 3. That'll give us a concave up into the second derivative there. And so concave up, let's go ahead and put that in from negative infinity up to 1. And from 2 on, we're concave down between 1 and 2. We do change in from concave up to concave down at 1. And then we change again from concave down to concave up at an x value of 2. So both of those Hilbert numbers actually end up being inflection points. So point of inflection at 1, comma, whatever. I'm going to throw that into my original function. And another inflection point at 2, comma, whatever. Again, I'm going to throw those into the original function, x times x minus 2 cubed. So let's throw the 1 in. 1 times 1 minus 2 cubed. I got 1 times negative 1 cubed. So I got negative 1. I throw 2 in. It looks like it's going to spit out 0. Let's go ahead and find our x-intercepts by letting y be 0. To find our x-intercepts, we let y be 0 in the original function. And so that'll end up being 0 and 2. That'll be our 0. So 0, 0, 2, 0. Let's find our y-intercept by letting x be 0. If I let x be 0, it'll spit out a 0 for y. All right, so let's start putting this on our graph. Our zeros are 0, 0. We've got 2, 0. The original function is decreasing and concave up. Is decreasing to a half. So I'm decreasing and I'm concave up until 1. So I'm decreasing. Ideally, I would throw in a value. Maybe I'd throw the 1/2 in and see what value I get on that, which it's a relative min, so it's negative 27/16. So it's about right here. So I'm decreasing to there. I'm also concave up clear until I hit 1. So I'm concave up, and I'm also increasing. I'm increasing between a half and 2. So I get an increase from here to here between a half and 2. But keep in mind between 1 and 2, I'm concave down. So I'm concave down till I hit 2. And then I got to go concave up, and I got to increase after 2. So I got to increase after 2, and I got to be concave up. Those are the things I got to draw or keep in mind here. And it kind of rolls like that type of deal. And that's a pretty decent graph if you were to plug that into your graphing calculator just to take a look at it. All right, let's do it for this, same thing for this next one here. Number one, we've got y equals 8x minus 9x to the 8 ninths. Let's take our first derivative. So we got 8 minus 9, and we got 8 ninths x to the 8 ninths minus 9 ninths, so negative 1 ninth. Most of those ninths cancel there. So first derivative is 8 minus 8 over x to the 1 ninth, or the ninth root of x. Where is this first derivative undefined? Where is y prime undefined? Well, if that x to the 1 ninth is equal to 0, so if x equals 0, right, if I take it to the 9th power on each side, that would be where it's undefined. Is it a critical point? Yes, because if you throw 0 into the original function, it is defined. there. So it is a critical point. Now, where is y prime equal to 0? So where does 0 equal 8 minus 8 over x to the 1/9? I'm going to add 8 over x to the 1/9 to both sides. So I'll have 8 over x to the 1/9 equals 8. Multiply both sides by x to the 1/9. Divide both sides by 8. So I have x to the 1/9 equals 1. I'm going to take both sides to the 9th power. So x equals 1 to the 9th, which is 1. So let's go ahead and run our first derivative test. So it's undefined here. The first derivative is undefined, so some like a sharp point, or maybe it has just a vertical asymptote there or whatnot, right? And then x equaling 1. So we're going to test around those. So let's throw in like y prime of -1. So I throw it into the original. So I got 8 minus 8 over the 9th root of -1. Well, the 9th root of -1 is -1. So I got 8 plus 8. So y prime of -1 is positive. So positive, so we're increasing. Throw in, I'd probably do it with my scientific calculator, but throw in y prime of 1/2, and you'll see that that thing is decreasing. Right? You just do it with a decimal. You can throw in 2 over here, and you'll see into your scientific calculator. Again, I'm plugging it into the first derivative there, and see that that is positive there. So our critical numbers were 0 and 1. We're increasing from -infinity up to 0, and then from 1 on, we're decreasing from 0 to 1. Looks like we'll have a relative max at 0. Throw that into the original function, and it'll spit out 0. We have a relative min at 1. Throw that into the original function, and it'll spit out -1. Again, you're throwing that into the original. Now let's go ahead, number 2, now that we have y prime equals 8 minus 8 x to the -1/9, let's go ahead and take the second derivative and find any potential Hilbert numbers here. So the second derivative of 8 is 0, derivative constant 0, so I got, and then minus 8, now we'll take the derivative of that x to the -1/9, I got -1/9 x to the -1/9 minus 1. -1/9 minus 9/9 is -10/9. And so we've got the second derivative is -8 times -1. I got a positive 8 9x to the 10/9. There's our second derivative. Where is this thing undefined? Well, it'd be undefined wherever at x to the 10/9 is equal to 0. So I take both sides to the 9/10. So x would be 0 would make that undefined. Is it a Hilbert number? Well, x being 0, remember, is defined in the original function, so it is a Hilbert number. And of course, regardless if it's a Hilbert number or not, we do want to test around it. So that's a Hilbert number. Now, where is y double prime equals 0? Well, if I let that be 0, 0 equals 8 over 9 x to the 10/9. I multiply both sides by 9x to the 10/9. I get 0 equaling 8. Well, that doesn't work, doesn't spit us anything out. So it looks like we're just stuck with the Hilbert number of 0 to test around. Let's go ahead and throw in y double prime of -1. So we got 8 over 9, -1 to the 10/9. And so that'll end up being a positive 1, right? -1 to the 10th power is positive 1. Positive 1 to the 1/9 is 1. So I got 8/9. So that ends up being positive, so we are concave up. I'm going to throw in y double prime of 1. I'll also see that that is positive. Again, feel free to use your scientific calculators as well on those. So we're concave up, and then we're concave up. We're concave up from negative infinity up to 0, and then we're concave up from 0 on. Concave down, not applicable here. No point of inflection, did not change concavity here. Not change concavity. Any zeros? Let's do our zeros now. Remember, our original function was 8x minus 9x to the 8/9. So, whereas y equals 0, let's take an x out. I'd have 8 minus 9x to the negative 1/9. So I have x equaling 0 and 8 minus 9x to the negative 1/9 equaling 0. And that's about 2.9 it looks like. So there's our x-intercepts at 0 and at about 2.90. Let's go ahead and put those on there. 0, 0, 2.9, about right there, 0. And then we're increasing to 0, and we're concave up, but we're increasing to 0, and it's pretty sharp. I mean, it'd be nice if you could throw some points in. And then remember, it's the first derivative is undefined at 0, so I'm going to have a sharp point. Now the point is defined there at 0, right? We have a relative max there is 0, 0. And then we hit this relative min at 1, negative 1. We're staying concave up again, but we've got a decrease between 0 and 1. So I stay concave up, but I got a decrease, and then I increase after 1, and I stay concave up. So that's a pretty decent graph of this function. Of course, you can compare it to your graphing calculator if you'd like. All right, for this one, we've got y equals x plus cosine x. We're just looking between 0 and 2 pi, though. Let's go ahead and take this first derivative. Derivative of x is 1. Derivative of cosine is negative sine. Let's see. It's not defined. The first derivative is defined everywhere, so let's just find out where it's equal to 0. Where does the sine of x equal 1? That would be at pi halves. So our first derivative test, now again, we're only looking between 0 and 2 pi, right? Because I know, like, for example, the sine of 5 pi over 2 is also 1, right? So that would be a critical point, but I'm stuck between 0 and 2 pi. So let's put that critical point on there. Pi halves. It is defined in the original function, so it is a critical point here. Let's throw in, I don't know, maybe like pi 6 or something, right? So I got 1 minus the sine of pi 6. Sine of pi 6 is a half, so that would be positive. So the original function is increasing up until pi halves. And maybe you want to just throw in like pi. Throwing pi would be a good one, right? After pi halves, something between pi halves and 2 pi into the first derivative again, and you'll see that that is increasing. So looks like we're increasing. Again, we've cut this off between 0 and 2 pi, right? So I'm going to go from 0 up until 2 pi halves. And then I'm also increasing again from pi halves, but I've cut it off until 2 pi. So that's how I'm going to say that. We're not decreasing anywhere. No relative extrema here, right? It's not like I increase and then decrease. I just increase and then increase. So no relative extrema. Let's go to our, now that we know the first derivative is 1 minus sine of x, let's see what Hilbert numbers we have. Let's take the second derivative. 0 minus derivative of the sine is cosine. So where's the cosine of x equal 0? And that would be at pi halves, and also at 3 pi halves. The cosine is 0. And remember, we're looking between 0 and 2 pi, right? So we've got pi halves on here, the 3 pi halves on here. Both of these are defined in the original function, so they are Hilbert numbers. And now we'll throw some points in. Maybe I don't know, pi 6 or pi thirds would be fine. So that ends up being negative. So we're concave down. Throw something in between pi halves, 3 pi halves. How about pi? Throw pi in. Negative cosine of pi, so negative negative 1, that's positive. And again, I'm throwing it into the second derivative, which is negative cosine of x. Throw something in between 3 pi halves and 2 pi, maybe 7 pi fourths or something. Throw that in, you're going to see that that is negative, so the original function is concave down. So we're concave up from pi halves up until 3 pi halves on that interval. And then we're concave down from 0 to pi halves, as well as from 3 pi halves to 2 pi. Okay. Do we change concavity? Yes. We change from concave down to concave up at pi halves. So pi halves is an inflection point. And then we change from concave up to concave down at 3 pi halves. And so I'll have to throw that into my original function. My original function is y equals x plus cosine of x. So y equals pi halves plus cosine of pi halves. So we got pi halves. Cosine of pi halves is 0. So that just spits out a pi halves. Throw the 3 pi halves in, and you're going to see that that's also spits out a 3 pi halves when I throw it into the original function. And then let's go ahead and find the, bless you. Let's find our zeros here. Where's the y value equals 0? I've got x plus cosine of x here. And we're just looking between 0 and 2 pi. Where's the cosine of x? Equal x, and so that'll give us nothing on that one. And then any y-intercepts. So let's let x be 0. So we got 0 plus cosine of 0 is 1. So we go y equals 1. So the y-intercept is the point 0, 1. 0, 1. And I'm trying to think, this may not be the best graph for this. I'm going to change this graph up here. Let me go pi halves, pi, 3 pi halves, 2 pi. So I got 0, 1. No x-intercepts on that. It looks like we are increasing from 0 to pi halves and we're concave down. So we're increasing 0 to pi halves and concave down. So we're increasing but concave down. And then we're concave up from pi halves to 3 pi halves, but notice we're increasing from the whole time from pi halves to 2 pi. So we're concave up, if you will, but and then we're increasing pi halves to 3 pi halves. Then we switch, but we're still increasing. We switch from 3 pi halves to 2 pi, we switch to concave down. So we kind of concave down. Of course, it'd be nice to throw in, I'd throw in those values to kind of get a little closer on my, throw 2 pi in, 3 pi halves pi, and so on. Make sure that your points are pretty accurate as far as the x, y values there, but it gives you kind of a decent curve sketch. And I think before we start this one, I'm going to write this in a form where I can just use the power rule instead of using the quotient rule, right? So let's go ahead and take the first derivative. We got 5. Let's take the first derivative. I got -1, x squared minus 1 to the -2. Chain rule, derivative inside, derivative of that x squared minus 1 is just a 2x minus 0. So our first derivative here ends up being -10x times x squared minus 1 to the -2. So y prime is -10x over x squared minus 1 squared. Where is this thing undefined? Where is y prime undefined? Well, we can't have that x squared minus 1 being 0, right? That would be problematic. Add 1, square root. So plus or minus 1 would make it undefined. Now, is it a critical point? Well, it's not. 1 and -1 make it undefined in the original. So technically, it's not a critical point. But when you run the first derivative test, you're still going to throw -1 and 1 on there, but just know that they're not defined in the original function. But I still want to test around them, so they're not technically critical numbers. Now, where is y prime equal to 0? Where is 0 equal -10x over x squared minus 1 squared? Multiply both sides by x squared minus 1 squared. You get 0 equals -10x. Divide both sides by -10. You get x equaling 0. So 0 is a critical number here, and it is defined in the original function. Okay, so now let's go ahead and we would test like y prime of -2. Throw that -2 in here, and let's see, you get a positive over a positive. Now notice the bottom is always positive. All right, -10 times -2. This -2 squared minus 1, because it's all squared, all right, the bottom's always positive. So you got y prime of -2 is a positive over a positive. So the original function is increasing. Let's throw in like -1/2. You're going to see that that thing's positive. You can throw it into the first derivative. Throw in +1/2. The original function decreases. Throw in maybe 2. The original function decreases again. So let's throw these on here. So we're increasing from -infinity up to -1, and then from -1 to 0. We're decreasing from 0 to 1, and from 1 to infinity. Now, number 3, we know our first derivative is -10x over x squared minus 1 squared. So our second derivative, I'm going to use the quotient rule. Derivative at the top times the bottom minus the top Derivative of the bottom, 2x squared minus 1 to the 1 power times 2x all over bottom squared. Okay. So this y double prime will end up being, if you clean all this up, you'll get 10 3x squared plus 1 all over x squared minus 1 to the 3rd power. Okay. So where is this thing? Where is y double prime equals 0? So where is 0 equal 10 3x squared plus 1? Well, that'd be 3x squared plus, I have to divide both sides by 10. So 3x squared equals negative 1, x squared equals negative 1/3. When I take the square root, I've got an imaginary number. Well, we're not working in the imaginary number, so we can forget about that. It does not pop out any potential Hilbert numbers. Whereas y double prime undefined, it would be undefined anywhere where this x squared minus 1 equals 0. So I either factor that or add 1 to both sides and square root both sides. You end up with 1 and negative 1. But these are not in the original domain, not in original functions domain. So they're really not Hilbert numbers. They're really not Hilbert numbers. And so we are going to test around them. So let's run our second derivative. Let's see, this is step number 4 here. Second derivative test, negative 1 and 1. But again, just remember the original function is not defined there. There's vertical asymptotes at x equaling 1 and x equaling negative 1. All right. And so let's go ahead and plug in like y double prime and negative 2. So I throw that into my second derivative here. It'll end up being positive, so we're concave up. Let's throw in like y double prime is 0. Again, throw that into the second derivative. You'll see that that is concave down. And let's throw in y double prime of 2. And you'll see that that's positive, so we're concave up on this. Okay. And let's go ahead and write down a few more of these items here. I should have mentioned we have from the first derivative, you see how we increase and then decrease at 0? So we have a relative max at 0. If I throw that into the original function, 5 over x squared minus 1, if I throw 0 into that, I get negative 5. So I have a relative max there. I don't have a relative min. Now let's go to our second derivative test. Our concave up, negative infinity, up to negative 1. And then we're also concave up from 1 on. We're concave down between negative 1 and 1. No points of inflection because those are not Hilbert numbers. Remember, those, even though it changes concavity at negative 1 and 1, I have vertical asymptotes there. I have vertical asymptotes. It's not defined at negative 1 and 1, so I can't have an inflection point. So that's not applicable on that. If I'm finding any, do I have any x-intercepts where y is 0 in the original function? Well, I multiply both sides by x squared minus 1. 0 is not equal to 5, so I don't have any x-intercepts on this. Do I have any y-intercepts? Yes. At when x is 0, y ends up, y-intercepts 0 and negative 5. Do I have any horizontal asymptotes? Well, the degree of the top is 0. The degree of the bottom is 2, x squared minus 1. So remember, for pre-calc, degree of the top is less than the bottom. You would automatically have horizontal asymptote y equals 0. Right? Or you can run that limit as x goes to infinity. If you run the limit as x goes to infinity, you'll also see you have horizontal asymptote y equals 0. And then let's draw this thing. So we're concave up, and we are increasing until -1. And, you know, ideally I'm going to throw some points in too, but we're going to be concave up and we're going to be increasing. I have this point 0, -5. That's a relative max, and I'm concave down between them. Remember, this is a rational function here. And then I'm concave up over here, and I'm decreasing. Again, throw some points in to be a little bit more accurate, but you kind of have an idea of what that graph would look like. Looks like we've got some conditions on this one. Let's take these ones first. F of -2 equals f of 2 equals 0, right? So they're giving us these points, -2, 0. They're giving us 2, 0, and they're also giving us 0, 4. Let's go ahead and throw those on there. -2, 0, 2, 0, and 0, 4. All right, so there's our points. Now, down below here, well, this line says f prime of -2 and f prime of 0 and f prime of 2 all equals 0, right? So those are our critical points, or potential critical points, as long as they're defined in the original. And if you notice above, they are all defined there, right? So that's where the slope of the tangent's equal to 0. And then it gives us the sign changes. So to the left of -2, it's negative. So we're decreasing. And then between -2 and 0, we're increasing. And then between 0 and 2, we're decreasing. And then after 2, f prime is positive, so then we increase. Right? So it's given us the first derivative test. And then down below, here, f double prime, here's our potential Hilbert numbers. F double prime of -1, f double prime of 0. Oops, actually that's a error. That's not supposed to be on there. Sorry about that. Just kidding. F double prime of 1 is 0, and then you see the table down below for the f double prime test. So it's going to be concave up to -1, and then it shows that it's concave down, and then it shows it's concave up. So let's see if we can't put this all together. We decrease to -2, but we stay, we decrease, but we're concave up. We decrease, but we're concave up until -1. But between -2 and 0, we're increasing. So we stay concave up. Then we switch to concave down between -1 and 1. And notice we have a relative max at 0, right? We have a relative min at -2. We have a relative min at 2. But we got to change concavity after 1. To concave up, but we still decrease to 2, and then we increase after 2, but we stay concave up. And that's a pretty decent curve sketch of that one. Let's do another one here on this next one. F of 2 equals 0, so 2 comma 0. 0, -3 right there. And then it gives us our first derivative on that. F prime of -1 is 0, f prime of 1 equals 0, and the sign changes, so we're increasing, and then we decrease, and then we increase. F double prime down below of 0 equals 0. We're concave down, and then it shows us that we're concave up with the table there. All right, so let's start out. We're increasing. Well, we're increasing to -1, and we're concave down until 0. So we're increasing to -1. Maybe something like this. We're increasing to -1, but I'm going to stay concave down. And now we have a max there at -1. Okay. Now we got to continue to decrease between -1 and 1. But I've got to change concavity. So I'm going to change to concave up. I decrease to 1. And then I have a relative min right there at 1. And then I increase through and I stay concave up. And that's okay, at least with the limited information that we have. It'd be nice if we knew exactly where the -1 value was and the 1 value was, but we just don't have that information as to where that relative max and relative min is located exactly, right? But that's a decent graph of that. Thanks so much for watching part 2 of this and taking notes. We'll see you next time.